Hello, good evening, everyone, and welcome back to another session in this revision session on refrigeration and air conditioning in the crash course. Today, we'll be revising the entire refrigeration and air conditioning subject. So, very good evening, Deepak Kumar Shah, Nagmani, Vikas Yadav. Very good evening. I'm perfectly fine, Perumala Nagmani, and I hope you have seen the last video on the revision of entire IC engine subject. In that session, we have revised the entire IC engine subject, and with not just revision, we have also solved 15 questions. Today also our idea is same. Today also we'll be revising the refrigeration subject, refrigeration air conditioning, and along with that we'll be solving some good questions based on the concept of refrigeration air conditioning. So everyone quickly join me for this session. Yes. Good evening, everyone. So we have right now how many students? We have 6 students live in the session. Guys, please quickly join me for this revision session on the refrigeration air conditioning subject. And as you know, the timing is fixed every day 7 p.m. Tomorrow we'll be revising the power plant subject. Okay, so entire fluid mechanics have been revised. Entire thermodynamics IC engine have been revised with practice of questions. Today we'll be revising the refrigeration air conditioning subject, along with we'll be solving some questions. Okay, so good evening, everyone. Good evening, those who have joined me for the session. Very good evening, everyone. I'm back again with another session in this revision crash course. Hi Deepu, very good evening. So I hope you guys are doing good and you guys are enjoying the revision session. And this session must be helpful for you for your preparation for GATE 2021 because it's only 1.5 months is left for your exam. So definitely this session are definitely helping you for your preparation of GATE exam. And those who have joined me for the session, please also spend some time to like the session and share the session, so that we can have more number of participants in this session. Hi Abhinandan, very good evening. Hi Sonali Kumari, good evening. Prateek, good evening. Krishna Kumar, good evening. When I will start late night series? The late night series will be started from 31st of December. That is from tomorrow onwards. Okay. So late night series will be started. I will be starting the subject of fluid mechanics in that. Okay. So good evening, everyone. I can see right now we have 14 students who are live with me, but this number is very less, my dear students. Come on, please, everyone, share this session to your Telegram group, or if you are joined in any group or WhatsApp, you can just share this session to your friends. Also, you can like the session if you have just joined our session, and if you have not yet subscribed our channel, then please do subscribe the channel also and press the bell icon so that you don't miss any videos from Grade Up. So good evening, everyone. Hi. From what timing? The timing of the late night series will be 11 p.m. Okay, that is the name. The name of that series is Qualified Series. In that, I will be teaching you the fluid mechanics, thermodynamics, and I will be teaching you each topics. Okay, some important topics of fluid mechanics and thermodynamics which are important for your GATE exam. Hi Hitesh, very good evening, welcome to the session. Hi Sarath Lal, very good evening, welcome to the session. Hi Thomas, good evening, welcome to the session. So I think we should start the session now. It's already 7:04, so I think we should start the session. So guys, I will be starting with the revision of the refrigeration air conditioning subject, and along with revision we'll be solving around 15 to 16 questions I have. Okay, so like we have done the revision of IC engine, very similar we can do that. Hi Nikhil Thomas, very good evening. सर गेट में वर्चुअल कैलकुलेटर माउस से यूज करना होता है. Hi Hitesh, yeah, definitely you have to use virtual calculator. For that you require mouse. They will be providing you mouse, right? Hi Harish Rathod, very good evening. Pranam, good evening. Can you give the class for heat and mass transfer on YouTube? Hi Deepu, the heat and mass transfer class will be taken by Suraj Gopi sir. He will be taking that subject. Okay. Yeah, you have to use mouse for using the virtual calculator. Okay, so shall we start the session? Are you ready, guys? Everyone? Shall we start? Yes, tell me, everyone. Are you guys ready for the session? I hope those who have joined me for the session, they have liked the session, because I can see we have 21 students live, but we have only 15 likes. So number of live and number of likes are not matching. So it's my request to everyone, those who have joined me for this session on revision of refrigeration air conditioning, please also like the session. Hi Akhilesh Khatse, very good evening, welcome to the session. Okay, so let's begin this revision on the refrigeration and air conditioning subject. Okay, let's start the revision. So I would like to start with my introduction. First, I am Vikas Sir. I have 5+ year teaching experience. I did my MTech in thermal engineering from Thapar University, and I have mentored more than 10,000 plus aspirants for different exams like GATE, ESE, SSC, My area of expertise includes subjects of fluid mechanics, thermal and applied, and heat transfer subject. When can I get SSC in grade up? Venkat, SSC in grade up is already there. Already we have a channel on SSC. You can join that channel. Okay, so now I'm going to start the revision of refrigeration air conditioning starting from the start. Okay, so if we talk about the subject of refrigeration air conditioning, I will be starting with the definition of refrigeration effect, because in refrigeration air conditioning this definition is very important. What is the meaning of refrigeration? Although in the subject of thermodynamics you have already studied about the meaning of refrigeration, it is a process of providing and maintaining a lower temperature than that of surrounding. Okay, suppose you have a system and you want to maintain the system at a lower temperature with respect to surrounding. This is the surrounding temperature. Now with respect to surrounding, if you want to maintain the temperature of this system, if this is your system and you want to maintain this system at a lower temperature with respect to surrounding, then that can be achieved with the help of a refrigeration process. Hi Akshay, very good evening. And the process of doing that, maintaining the system at a lower temperature, this process will be called as refrigeration effect. It is also called as cooling effect. Okay, it is also called as cooling effect. Clear? Or sometimes you can also call it as desired effect, because in the thermodynamics you have studied about the COP, coefficient of performance. It is desired effect divided by work input. Okay, hi everyone, very good evening. Next is coefficient of performance. All the basically work absorbing devices. For the work absorbing devices like a refrigerator and heat pump, the performance is measured with the help of a parameter called as coefficient of performance, called COP, which is equal to ratio of desired effect to work input. COP is also equal to the refrigeration effect divided by work input. Okay, so these things you maybe already knowing about this, but still because we are revising everything, so I'm telling you everything from start. You can call it as refrigeration effect divided by work input, or you can say desired effect by work input, or cooling effect divided by work input. Okay, this is called as COP, coefficient of performance. Clear everyone? Yes, is it clear? Okay with everyone? Now next is the unit of refrigeration. We have understood what is refrigeration effect. We have understood what is COP, coefficient of performance. Now let's understand what is the unit of refrigeration. The unit of refrigeration is basically TR, tons of refrigeration. You can call it as ton of refrigeration. That is a unit of refrigeration. And the definition of unit of refrigeration basically comes from basically a method which was used in the USA and the Western countries to cool the houses in the summer. And for maintaining those houses at a lower temperature, they used to bring some water tank, and they used to spray the water on the houses in order to maintain them at low temperature. Okay, so in doing so they required around 1 ton of water for maintaining the houses at lower temperature. And this is how the idea of unit of refrigeration came. The idea of unit of refrigeration came from this thing, that how much amount of water was required to extract the heat from those houses in that country. It is not, the ton and tonnage is different. This is ton of refrigeration. Okay, tonnage is the unit of weight. Okay, that ton is the unit of weight. This is meaning of ton of refrigeration. That is another thing. Okay, the tons of refrigeration, or TR, it is a unit of refrigeration. 1 ton of refrigeration is equal to 3.5 kilowatt. 210 kilojoule per minute or 50 kilocalorie per minute. So you have to remember this conversion is also very important, that 1 ton of refrigeration can be written as, how possible refrigeration effect more than work input? It is possible, Naveen, it is possible because we are giving work input. If you give work input, you can do anything. If you pay, if you give money, you can buy all the essential commodities, right? So if you pay money, if you are giving work as input, definitely you can extract more cooling effect. Like in the case of refrigerator. In the case of refrigerator, domestic refrigerator, your COP is always greater than 1. Why? Because in case of refrigerator, you give work as input to get the cooling effect. Okay, so obviously your COP will be greater than 1 for a refrigerator, and so refrigeration effect is greater than the work input. Okay, because that is our requirement. If you are not getting proper refrigeration effect by giving work as input, then what is the point of giving work as input? Okay, because the whole idea is to give work as input with the help of a compressor and take out cooling effect. Okay. Yes, entire power plant will be revised tomorrow. Yes, exactly, correct. Now we are going to understand what is vapor compression refrigeration system. Well, vapor compression refrigeration system is a working cycle. It is a working system of, it is the working system of a domestic refrigerator. Domestic refrigerator are based on, domestic refrigerator are based on the vapor compression refrigeration system. Domestic refrigerator means the refrigerator that you use in your houses. They are basically based on vapor compression refrigeration system. So what is the meaning of this vapor compression refrigeration system? In this particular system, basically vapor, refrigerant is the working substance. Refrigerant, it is a working substance. It is a working substance used for refrigeration. Working substance used for refrigeration is called as refrigerant. Okay, so in the case of a vapor compression refrigeration system, revised Carnot cycle and VCR are the same. No, why they would be same? It is not revised, it is reverse Carnot cycle, Thomas. Okay, reverse Carnot cycle is the standard cycle for all the work absorbing devices, whether it is a heat pump or it is a refrigerator. Okay, vapor compression refrigeration system is, although it is the working cycle of a domestic refrigerator, we can say that. Okay, so in this, the refrigerant basically will be in the vapor form, and also it will be changing its phase. So what are the major components of a vapor compression system? It will be having a compressor, it will be having a condenser, a expansion valve. Particularly we use a capillary tube here as an expansion valve, which is a throttling device here. Okay, as you know that capillary tube is a throttling device, so that is what we are using in the vapor compression system. And finally, in an evaporator. Evaporator is that component where cooling is produced. So cooling is actually produced in the evaporator. Okay, so how this thing works? Basically, in the case of vapor compression system, in the evaporator we will be having a liquid refrigerant. Liquid refrigerant in the form of a liquid refrigerant will be there in the evaporator, and that liquid refrigerant, what is the purpose of that liquid refrigerant? It is used to absorb the heat from that place which has to be maintained at a low temperature. So this evaporator, which is containing some liquid refrigerant, it will absorb the heat from your food items, from your basically your fruits, vegetables, whatever things you keep in your refrigerator, let's say. It will absorb the heat from those items, and when it will do so, the liquid refrigerant will get evaporated. Because it will absorb the heat, it will get evaporated. There will be a phase change process, and that is why this is also called as evaporator, because the liquid refrigerant inside the evaporator will get converted into vapor. So in vapor compression system, we say that the vapor coming out of evaporator has to be saturated vapor. Saturated vapor means that vapor which is at the point of saturated vapor line, that is called saturated vapor. Okay, which has just converted into vapor, that is called saturated vapor. Okay, now This saturated vapor will go into a compressor. Compressor is a device which is used to increase the pressure and temperature of this saturated vapor. So it will increase the pressure and temperature. It will make it superheated vapor. Okay. Now on this superheated vapor will now go into the condenser. Condenser is a heat exchanger which is used for rejecting the heat of this vapor. It will reject the heat of the vapor and also it will convert this vapor into liquid. Which liquid? Saturated liquid. Now this saturated liquid will go inside the expansion valve, which is also a throttling device. When I have taught you the topic of thermodynamics, in that thermodynamics subject I have taught you the Joule-Thomson coefficient, right? So in that I have told you that in Joule-Thomson experiment we are having two curves. One was for cooling, one was for heating. So in the case of expansion valve or capillary tube here, both temperature and pressure will drop. Temperature and pressure will drop in the expansion valve because expansion valve will be a capillary tube. It will be having a throttling process. So in capillary tube we will be having a throttling process. Throttling means isenthalpic expansion. This is very, very important. We will be having isenthalpic expansion in the capillary tube. Okay. So isenthalpic expansion will take place in the capillary tube and the pressure and temperature of the liquid will get decreased. Okay. After that, this at low pressure and temperature, this liquid will be sent into the evaporator. Now the point is, this expansion valve, while it converts the liquid into at low pressure and temperature, some part of the liquid also get converted into vapor. So at the output of the expansion valve, you will be getting the mixture of liquid plus vapor. This mixture of saturated liquid and vapor will come out of expansion valve. Now the point is, inside the evaporator, only liquid refrigerant should go. Why? Because evaporator will produce good cooling if only liquid refrigerant is sent into the evaporator. Okay. Which refrigerant is used for the VCR cycle? In VCR cycle, back home we use different types of refrigerant, but in the case of domestic refrigerator, we use R134. Nowadays we use R134, but before that we were using R12 as a refrigerant. Okay. Why we use R134? Because R134 is an eco-friendly refrigerant. It does not contain any chlorine atoms, so that it cannot cause any ozone layer depletion problem. Okay, कितनी देर class चलेगी? Class will go when the topic will be completed, the class will be completed. Okay, so timing is never a constraint for me because my main idea is, because my main intention is to cover the entire revision with practice of questions. Okay, I don't know how much long the class is going to take place, but we will be completing the whole thing that I have brought for the class. Okay. So saturated liquid plus vapor mixture will come out from this expansion valve, but we have to send only liquid refrigerant to the evaporator. So for that we require a flash chamber. We require a flash chamber at this point. The flash chamber is a device which is used to separate the liquid and vapor refrigerant. Okay, now this flash chamber will be separating the liquid. Liquid will settle in the bottom. This liquid will be sent to the evaporator and the vapor will come out from the top. This vapor will go to the compressor. So vapor will be sent to compressor and liquid will go into the evaporator. So we'll be using a flash chamber, but flash chamber is not a part of vapor compression cycle. Okay, yes, it is required for basically separating the liquid and vapor refrigerant, but it is not represented in the vapor compression cycle. In vapor compression cycle, we'll be seeing only four components: compressor, condenser, throttling device or capillary tube, and evaporator. Okay, so this is how the cycle will go. Now in the vapor compression cycle will be represented with, this is how we will be representing the vapor compression cycle on temperature entropy diagram. So in the vapor compression cycle, this is the temperature entropy diagram will be, so let us say this is point 1. This is point 1. At point 1, the saturated vapor. See, there are important assumptions. There are some assumptions of vapor compression cycle, and these assumptions are: the entry to the compressor should be saturated vapor. Okay, this is a very important assumption of a vapor compression cycle. And at exit of condenser should be saturated liquid. These are the two important assumptions of a vapor compression cycle, simple vapor compression cycle. That entry to the compression should be a saturated vapor, that is at this particular point. This is the point of saturated vapor, and this is a compression in the compressor 1 to 2, isentropic compression. Then we'll be having this is the point 2 and this is the saturated superheated vapor. Then we will be sending this into the condenser. This is the condensation from 2 to 3. Then at this particular point 3, we will be getting saturated liquid. Now this saturated liquid will go into the throttling device. 3 to 4 is throttling or isenthalpic expansion, and 4 to 1 will be the heat supplied in the evaporator. So this is how the process are given. Oh my God, Naveen, we are here not going to discuss about your general questions regarding all this. We are basically revising the refrigeration air conditioning. If you are having any general question like that, my dear, then you can definitely ask me, okay? Because we are not here preparing for any interview or something like that. Here, the main intention is to crack the GATE exam. And for GATE exam, you have to revise the important concept and formulas, okay? Now you are still stuck up at that point why we get more desired effect in the refrigerator. Please move over on that and let's focus on here because we have more important thing to cover here. Okay, so at point 2 we'll be getting the superheated vapor. Now this superheated vapor will be sent into the condenser. Okay, in the condenser heat rejection will take place. Then there will be throttling process. Okay, this is condenser, this is evaporator. This is temperature entropy diagram. In pressure enthalpy diagram, this is the pressure of the condenser, this is the pressure of the evaporator. So it will be working between two pressure. One is condenser pressure, this is the high pressure, and the other is evaporator pressure, which is the low pressure. So 1 to 2 is the compression in the compressor. Then we have constant pressure heat rejection. Then we have isenthalpic expansion 3 to 4. The enthalpy at the point 3, enthalpy at point 3 will be equal to enthalpy at point 4. Remember that. Now this is a very important point here. Enthalpy at point 3 should be equal to enthalpy at point 4. Now what is the COP? COP of this vapor compression system is equal to H1 minus H4 divided by H2 minus H1. Because COP is equal to what? It is equal to refrigeration effect divided by work input. This is the formula for COP of a vapor compression system. So you have to remember this formula. Refrigeration effect is produced in the evaporator, that is between 4 to 1. Okay, so the refrigeration effect will be H1 minus H4. Okay, and heat is work input take place between compressor, that is 2 to 1. So that will be H2 minus H1. Clear? So this is how you find the COP, but sometimes they don't give you the value of H4. So what you have to do? In that case, your COP will be equal to H1 minus H3 divided by H2 minus H1. If H4 is not given, then you have to remember that H3 is equal to H4. You have to remember this thing. Okay, so this is a very important point of vapor compression system. Sometimes in your exam they will not give you the value of H4. So you have to put the value of H3 because H3 is equal to H4. Remember that. Okay, because 3 to 4 is the isenthalpic process in the vapor compression system. Clear? Now there is a very important point of wet compression, dry compression. What is the meaning of wet compression? Simple meaning of wet compression is that in the compressor, if your refrigerant is going into the compressor from this point, this is the point of wet region. It is liquid plus vapor region. That is, if the entry to the compressor is from this point, this is the point of entry to compressor. That is, this will give you the wet compression. That is, wet compression means inside the compressor, liquid plus vapor mixture is going inside the compressor. That is called wet compression. But generally, you know that in your compressor, you do the dry compression. That is, compression should be at this particular point. This should be the point of compression. This is 1 dash, 2 dash. This should be the compression. That is, we require dry compression. So this is dry compression. Dry compression means only saturated vapor goes into the compressor. Wet compression means liquid plus vapor mixture goes into the compressor. So what is the disadvantage of that? The main disadvantage is that the refrigeration effect will reduce. Okay, and another disadvantage is that inside the compressor we have some lubricant to protect the compressor from wear and tear. Now if liquid plus vapor mixture goes into the compressor, some of the lubricant can wash away along with the liquid refrigerant to the condenser and in the further components of the cycle, and because of that it can cause wear and tear of compressor. Okay, so the liquid refrigerant might wash away some of the lubricant, and this can cause wear and tear of the compressor. So these are the basically disadvantage of wet compression. That is why we use dry compression in the vapor compression system. Now we have also very important formula of volumetric efficiency of a compressor. There are few important points that I have to share with all of you, that volumetric efficiency of a reciprocating compressor is also equal to 1 plus C minus C P2 by P1 over 1 by N, where P2 you know higher pressure is P2 and P1 is the lower pressure. With this is the clearance ratio, C is equal to Vc by Vs. It is also called as clearance ratio. So this is a very important formula of volumetric efficiency. Now volumetric efficiency, like I have told you, it is the ratio of actual volume divided by stepped volume. So volumetric efficiency can also be written as mass flow rate of the refrigerant into specific volume at entry to the compressor, that is V1, divided by stepped volume, which is pi by 4 d square L n k by 60. This is the formula of. So volumetric efficiency can also be written as mass of the refrigerant into specific volume at entry to compressor divided by pi by 4 into d square into L into n into k divided by 60. This is the formula for volumetric efficiency of a reciprocating compressor. This is also the formula. This is also the formula. But what is the difference between these two formulas? This is the formula only for a reciprocating compressor. Okay, this is the formula for volumetric efficiency of a reciprocating compressor. As you know that compression are of different type. It can be reciprocating compressor, it can be rotary compressor, it can be dynamic compression. In that we have centrifugal compressor. Okay, so for a centrifugal reciprocating compressor, this is the formula for volumetric efficiency, and we can also write this in terms of mass flow rate of the refrigerant into specific volume at entry to the compressor divided by stepped volume. This is the stepped volume. Okay, remember this formula of volumetric efficiency. Clear everyone? Is it clear to everyone? Now we are going to understand some of the parameters which affect the performance of vapor compression cycle, and these parameters are basically decrease of the what will happen to the COP of a vapor compression cycle if the condenser pressure is increased or evaporative pressure is decreased. Suppose that we are having the suppose we want to study the effect of decrease of the condenser pressure. If let us say this is the condenser, this is the normal VCR cycle. Okay, this is the normal VCR cycle. Okay, 1, 2, 3, 4. Now if we decrease the condenser pressure, then what will happen? If condenser pressure is decreased, then you can see clearly that this is the point 1, this is 2, this is 3, 4. So work input to the compressor will increase. Work input will become 1 dash to 2 now, and refrigeration effect will decrease, and same effect will be for increase of the condenser pressure. Okay, if condenser pressure is increased, if I increase the condenser pressure, then refrigeration effect will decrease, and the work input will now increase. Okay, so these are the two effects which are same for decrease of the evaporator pressure and increase of the condenser pressure. This is the effect of increase of condenser pressure, and this is the effect of decrease of evaporator pressure. So if you decrease the evaporator pressure, your refrigeration effect will decrease, your work input will increase. So what will happen to COP? Your COP will decrease. So these are the common effect of decrease of the evaporator pressure and increase of condenser pressure. One more important effect is, as we can clearly notice, that the pressure ratio is also increasing if you decrease the evaporator pressure and increase the condenser pressure. If pressure ratio will increase, the volumetric efficiency is equal to 1 plus C minus C P2 by P1 over 1 by N. So if this pressure ratio will increase, the volumetric efficiency will decrease. Now what is the effect of volumetric efficiency? Volumetric efficiency, if it decreases, then you have to supply more refrigerant inside the compressor for producing more refrigeration effect if your volumetric efficiency decreases. So that is a very important thing, that volumetric efficiency decrease means you have to supply more mass flow rate of refrigerant. Next is the effect of superheating. Okay, superheating within the evaporator. If you are doing superheating within evaporator, then what is the effect of this thing? See, superheating within evaporator simply means that, so this is a normal cycle. This is a normal cycle, and we are doing a superheating, and then we are doing this. Basically, the refrigerant goes into the evaporator, the compressor. So this is the normal cycle 1, 2, 3, 4. Okay, and this is the after superheating 1 dash 2 dash 3, 4. Now, if you see, you will find that with superheating, refrigeration effect is increasing. But what about the work input? You will see that work input is not getting affected, but actually work input is affected, because with superheating, work input will increase because the temperature T1 will increase. Temperature at the inlet to compressor will increase with superheat. That is, this temperature will increase because you know that compressor, the work input is also equal to N by N minus 1 MRT1 or MRT1 of P2 by P1 over N minus 1 by N minus 1. This is also the formula for the work input of a compressor. So we can simply say that the work input is directly proportional to the temperature at the inlet of the compressor. Because temperature at the inlet is increasing, the work input will also increase. That is, with superheating, the work input is also increasing and refrigeration effect is also increasing. So what will happen to the COP? So with superheating, there is a very important effect that with superheating in the evaporator, COP can increase or decrease depending on the refrigerant. For R12 refrigerant, COP will increase with superheating, and for ammonia as a refrigerant, COP will decrease with superheating, and for R12 COP will increase with superheating. So that is a very important thing, that with superheating the COP depends on the type of refrigerant. Okay, clear everyone? Is it clear? Next is a very important thing, and that is the effect of subcooling or undercooling. You can call it as subcooling or undercooling. What is the effect of this parameter? See, subcooling or undercooling means that generally you know that in your condenser, from your condenser, the liquid that comes out is a saturated liquid, right? This is what happens. But if we suck this liquid of the condenser and if we send this liquid into the compressed liquid region, that is this region which is compressed liquid or subcooled liquid, this is also called subcooled liquid region. And now if I do the expansion, so you can clearly notice that if you do the subcooling, this is called subcooling, that is reducing the saturation temperature of the liquid and sending it into the compressed liquid region or subcooled region. So what is the effect of that thing? The simple effect is that the refrigeration effect will increase. Work input is same, it is not affected. Work input is same, refrigeration effect will always increase. So COP will always increase with subcooling or undercooling. Okay, clear everyone? These are some important things you have to understand. Use of flash chamber. When you use a flash chamber is only used to separate the liquid and vapor refrigerant so that it can send only liquid refrigerant to the evaporator and it can send vapor refrigerant to the compressor. It is the only purpose of a flash chamber. It has nothing to do with the COP of the COP. Okay, it has nothing to do with the COP of the VCRS cycle. So with flash chamber, the COP will not be affected. Now we have also an important point called as cascade refrigeration. Okay, because sometimes this question can come from cascade refrigeration. See, cascade refrigeration, it is basically used for achieving very low temperature. And how do we, very low temperature of around minus 80 degrees Celsius to minus of 140 degrees Celsius. This low temperature can be achieved by a cascade refrigeration. Now this low temperature is required in the medical application, in the cryogenics, in medical application, your DNA, RNA are basically preserved and your blood samples, your blood cells are preserved at a very low temperature. So these cascade refrigeration is basically used for ultra low freezers. So what do we do in the cascade refrigeration? We combine two vapor compression cycle in series such that the evaporator of the upper cycle becomes the condenser of the lower cycle. This is called as cascade refrigeration. We combine two VCRS cycle such that evaporator of upper cycle becomes condenser of lower cycle. Or we can say that the condenser of the lower cycle will rejects its heat to the evaporator of the upper cycle. So the lower cycle will produce, lower VCRS cycle will produce very low temperature, very low temperature. Okay, this is a very important difference of cascade refrigeration. Now in cascade refrigeration, the COP of a cascade refrigeration is equal to COP of the any of the two cycle, product of COP of the cycle plus 1 plus COP of the cycle, COP of the two cycles. The COP of a cascade refrigeration is equal to COP of the lower cycle or higher cycle divided by 1 plus COP of the lower and upper cycle. Okay, this is the purpose of cascade refrigeration. Now let us move on to the vapor absorption refrigeration system. Vapor absorption refrigeration system is a system which is basically used in those places where the cost of electricity, it is used where cost of electricity is high. Okay, exactly, Deepak, that is correct. Cost of electricity is high, or where heat is abundantly available. Okay, like it is also used in the solar refrigeration. Like in solar refrigeration, we use the vapor absorption refrigeration. Okay, so this is a type of refrigeration system where we don't use a compressor because it is used in those places where electricity is either not there or electricity is very costly. In those places we use vapor absorption refrigeration system. So it is only that this type of refrigeration system where COP is less than 1. COP is generally never less than 1, but for a vapor absorption system, COP is less than 1 because in the vapor absorption system, we don't use a compressor. Why? Because compressor requires electricity and we cannot provide electricity for the compressor because this is a system which is used in those places where electricity is either not available or it is very costly. Okay. For example, for achieving solar refrigeration, we use vapor absorption cycle. In vapor absorption cycle, all the components are same. That is, evaporator will be there, expansion valve will be there, or throttling device will be there, condenser will be there. Only thing is that compressor will be replaced by generator, pump, and absorber. These are the three components will be replaced in the vapor absorption cycle. So in vapor absorption cycle, we don't use only a refrigerant. We use a combination of refrigerant and absorbent. A combination of refrigerant and absorbent is used. Okay, in the vapor absorption cycle, we use a combination of refrigerant and absorbent. Generally, we use two combinations. One is ammonia, water. Another is lithium bromide and water. Okay. The simple logic is that in the ammonia water system, ammonia is the refrigerant and water is the absorbent. And in the lithium bromide water refrigeration system, vapor absorption system, water is the refrigerant and lithium bromide will be acting as an absorbent. So basically the main idea of this thing is that will be taken as a refrigerant which will be having low boiling point. Refrigerant will be selected in such a way that it has low boiling point. So among ammonia and water, ammonia has low boiling point, and among lithium bromide and water has low boiling point. Okay, so that will be selected as a refrigerant which has got low boiling point. So this has got low boiling point. Okay. So in this refrigeration system, absorber is that component which is used to absorb the heat of the refrigerant coming from the evaporator. So let us say we are using ammonia water system. So in ammonia water system, basically the saturated ammonia will come here. Saturated ammonia will come, and in the absorber will be having the weak solution. Of ammonia plus water. Now this weak solution of ammonia plus water, when this ammonia will enter in the absorber, this heat of the ammonia will be absorbed and this ammonia will change into liquid with the help of water, and this mixture of ammonia and water will be sent with the help of a pump to the generator. In the generator, heat will be supplied in the generator, and this ammonia liquid will change into vapor because ammonia has low boiling point than water. Some of the water will also try to change into vapor, but that will be separated by analyzer and rectifier. These are the two components which do not allow the water to go in the condenser. Okay, analyzer and rectifier. Analyzer is basically like a fractional distillation, and which basically separate the water vapor if it tries to go into the condenser. And rectifier is like a shell and tube heat exchanger. It is like a shell and tube heat exchanger, and it acts as a condenser actually. It acts as a condenser which is used to separate the liquid, separate the water, so that only ammonia vapor, superheated vapor will be allowed to go into the condenser. In the condenser, same thing will happen. This ammonia vapor will change into liquid, saturated liquid ammonia, which will be sent to the expansion valve where the pressure and temperature will reduce. It will be sent to evaporator. Now this evaporator will be used for cooling application. So there are three important components. One is condenser where heat will be rejected. One is the absorber where heat will be rejected. One is generator where heat is supplied, and one is evaporator where heat is supplied. Okay. So if you have to find a COP of a vapor absorption system, so you have to remember that in generator heat is supplied, in evaporator heat is supplied, and condenser and absorber will be rejecting their heat to surrounding, to the atmosphere. So if you apply the energy balance, that is the heat supplied, Qg plus Qe will be equal to heat rejected, which is Qc plus Qa. Okay, hi Om Prakash, very good evening. This is the total heat supplied. This is the total heat supplied. In the evaporator and generator, this is the total heat rejected. Net heat supply is equal to total heat rejected. So if you have to find the COP of a vapor absorption system, it is equal to heat supplied in evaporator divided by heat supplied in generator. It is heat supplied in evaporator, heat supply in evaporator divided by heat supplied in generator. This is the formula for the COP of a vapor absorption system. If we have to find the COP, so we have to use just 3 temperature. We require 3 temperature, TG, which is the generator temperature. Okay, we require 3 temperature, generator temperature. We require the evaporator temperature, and we require the surrounding temperature. These 3 temperatures are required to find the COP. So COP can be found using this formula also, and COP can be also found using this formula. 1 minus, between these 2 temperatures you have to apply the formula for efficiency of a Carnot cycle. 1 minus T0 by Tg. And between these 2 you have to apply the formula for COP. This will be Te by T0 minus Te. Okay? Clear everyone? So basically, if whenever question comes from COP of vapor absorption system, you have to find only 3 temperature: generator temperature, evaporator temperature, and surrounding temperature. Between the generator temperature and surrounding temperature, between these 2 temperatures, you have to apply the efficiency of the Carnot cycle. Carnot cycle efficiency will be applied between T0 and Tg. And between evaporator and surrounding, you have to apply the formula for refrigerator. COP of refrigerator, Carnot refrigerator. Clear? Just multiply these 2, you will be getting the COP. This is how you will be finding the COP of a vapor absorption system. So whenever a question comes from COP of vapor absorption system, you have to find the 3 temperature: TG, highest temperature, then T0, second highest, and the lowest temperature is TE. You have to just find these 3 temperature. And the temperature here should be kept in Kelvin. All the temperatures should be in Kelvin. This is important. Temperature should be in Kelvin only. Clear everyone? So this is how you will be finding the COP of a vapor absorption refrigeration system. Clear everyone? Yes, is it clear to all of you? Please tell me. Yes everyone, tell me. Clear? So if it is clear, we can move on to the next topic, which is the gas refrigeration. Okay, now gas refrigeration is also called as air refrigeration. You can call it as gas refrigeration or air refrigeration, gas refrigeration or air refrigeration, or you can also call it as the working cycle of a gas refrigeration is basically Bell-Coleman cycle, reverse Brayton cycle, or reverse Joule cycle. Why it is called reverse Joule cycle or reverse Brayton cycle? Because the process in this cycle are exactly same as Brayton cycle, but they act in the opposite direction, in anti-clockwise direction. This is a Brayton cycle in anti-clockwise direction because it produces refrigeration effect. Okay, so it is basically the Brayton cycle acting in anti-clockwise direction, my dear. It will be having 1 to 2 as isentropic compression in compressor. It will be having isentropic compression. Then it will be equal to 2 to 3. It will be constant pressure heat rejection. Now here important point is that in gas refrigeration, the working refrigerant is gas, and we will treat it as an ideal gas. Working refrigerant is ideal gas. We will be treating it as an ideal gas, and for ideal gas, enthalpy is a function of temperature only. So remember this thing. So next is constant pressure heat rejection in a cooler. We'll be using a cooler, not a condenser here. Then we'll be using 3 to 4 isentropic expansion. We'll not be using a throttling device here. We'll be using isentropic expansion. We'll be using an expander, not a throttling device. Why? I have told you in thermodynamics that throttling process is never done for an ideal gas, because if you do throttling of an ideal gas, then it will not decrease the temperature. Pressure will be decreased, but temperature will not be decreased. Temperature will be same. So because we are using an ideal gas here, we will not be using a throttling process, we'll be using isentropic expansion, not isenthalpic expansion, sorry. So 4 to 1 will be constant pressure heat addition. Constant pressure heat addition. These are the process we study in the refrigeration cycle, Bell-Coleman cycle or reverse Brayton cycle. So basically all the process are same that we study in the Brayton cycle, but the cycle act in anti-clockwise direction. The COP will be equal to 1 by Rp gamma minus 1 by gamma minus 1. This will be the formula of the COP of a reverse Brayton cycle or reverse Joule cycle or Bell-Coleman cycle. But this formula can only be applied if compression and expansion are isentropic. This formula can only be applied if compression expansion is isentropic. If they are not isentropic, you cannot apply this formula. Okay, because only for an isentropic process you will be getting this formula. COP can also be written as 1 by T2 by T1 minus 1 equal to 1 by T3 by T4 minus 1 equal to 1 by Rp over gamma minus 1 by gamma minus 1. You can write the COP in any of these forms. All the forms are correct. Because ultimately in the vapor, in gas refrigeration, T2 by T1 is equal to T3 by T4 is equal to pressure ratio over gamma minus 1 by gamma. This is a very important point. Is it clear to everyone? In the vapor, in this gas refrigeration cycle, the COP, if the compression and expansion is isentropic, then you can apply any of this formula for finding the COP. Because T2 by T1 is equal to Rp, pressure ratio over gamma minus 1 by gamma, so ultimately you'll be getting this COP. Clear? Is it clear to everyone? Now there is also a very important term. Hi Akash Gautam, good evening. Welcome to the session. It is an important term called heat rejection ratio. Heat rejection ratio is equal to heat rejected. It is equal to heat rejected in condenser. Heat rejected in condenser divided by refrigeration effect. Refrigeration effect. Now you must be thinking, sir, heat rejection ratio is also equal to 1 plus 1 by COP. How you are getting this formula for heat rejection ratio? Actually, you will be getting this formula because you know that heat rejected minus heat supplied is equal to work input. Right? Heat supplied is actually equal to refrigeration effect. In the case of a refrigeration device, heat supplied is equal to what? Refrigeration effect. So we can simply say that your heat rejected is equal to work input plus refrigeration effect. So heat rejection ratio is equal to what? Heat rejected, which is equal to work input plus refrigeration effect divided by refrigeration effect, which will give you 1 plus work input by refrigeration effect, which is equal to 1 plus 1 by COP. Ultimately, you will be getting this formula. Clear? Is it clear to everyone? Is there some buffering issue, Neeraj? Is there any buffering issue? Please tell me, everyone. Is there any kind of buffering issue? Hi Anupam Bhunia, very good evening. If anyone has joined the session right now, please also like the session and share the session also. Hi Zafar Alam, very good evening. If anyone has joined the session now, please like the session and also share the session. So my dear students, this is a very important formula of a gas refrigeration cycle. Now I have told you a very important thing, my dear. COP of a gas refrigeration system is equal to this if compression and expansion is isentropic. What if compression and expansion are not isentropic? What if they are polytropic? Then how can you find the COP? Yes, if compression and expansion are not isentropic, then how can you find the COP of a gas refrigeration system? It is very simple, my dear. Thank you so much. Thank you so much, Zafar, for attending this session, because there is no use of this session if you guys don't come to the session. So actually it is basically maybe we are providing you this session that is helping you, but ultimately you are coming to the session. That is also a very important thing. So I hope this session are helpful for all of you. Let us say the compression and expansion are polytropic. Let us say this PV power 1.1 is equal to constant or P power 1.2 is equal to constant. They are polytropic. Let us say they are polytropic. We are having polytropic compression and expansion. Then how can you find a COP in gas refrigeration? Then you cannot apply the formula of the COP. So how can you find the COP then? Then the COP will be equal to refrigeration effect divided by net work input. Net work is equal to refrigeration effect divided by compressor work minus turbine work. Compressor work will be equal to what? N by N minus 1 P1 V1 N by N minus 1 P1 V1 minus P2 V2. And turbine work will be equal to N by N minus 1 P3 V3 minus P4 V4. This will give you the compressor work and turbine work. Okay, so from here you have to find the compression turbine work. Just put the value of compression turbine work here. Refrigeration effect will be equal to, refrigeration effect can be simply equal to what? That is H1 minus H4, I think. Yeah, that is equal to H1 minus H4. So it will remain H1 minus H4, but this you have to find. This you have to find by finding compressor work and turbine work, because you cannot apply the formula there. Okay, so you have to solve by normal method. You have to find the compressor work, you have to turbine work, and then you have to solve the question. Clear? Now let's come to the last topic of refrigeration air conditioning, which is air conditioning. Air conditioning is basically one more important thing in this gas refrigeration. Although it is, you will study that in the Brayton cycle also. In gas refrigeration, sometimes the compression and expansion are not isentropic, and they give you the isentropic efficiency. What is isentropic efficiency? Due to friction, the expansion and compression is sometimes is not isentropic, it is actual. This is, let us say this is actual and this is isentropic. This is isentropic, this is actual. So 3 to 1 to 2 is actual compression. Actual compression. And 1 to 2s is isentropic compression. Sometimes in your exam they will give you the value of mechanical efficiency or isentropic efficiency in the both compression and turbine. Similarly, 3 to 4 is actual expansion. Actual expansion. And 3 to 4s is the isentropic expansion. So when they will give you these formula, or when they will give you the isentropic efficiency, they will give you in the exam the isentropic efficiency of compressor equal to 0.8, and let us say for turbine is equal to 0.85. They will give you the isentropic efficiency of compression turbine. So you have to remember that isentropic efficiency of compressor is equal to isentropic work of compressor divided by actual work. So isentropic work will be equal to H2S minus H1 divided by actual is H2 minus H1. Hi Shubham, very good evening, welcome to the session. And isentropic efficiency of turbine is equal to actual work divided by isentropic work. Because in actual condition, your turbine will be giving you the less work as compared to an ideal condition. Because isentropic is the ideal case. So this will be H3 minus H4 divided by H3 minus H4S. So whenever they will give you these efficiencies, whenever you will be getting these efficiencies, you have to, whenever you will be getting these efficiencies, you have to do one important thing. You have to apply the formula. Okay, you have to basically find the actual work. You have to find the actual work, okay, by dividing the isentropic work by isentropic efficiency of compressor. And for turbine, you have to find the actual work by multiplying the efficiency with isentropic work. And then you have to put the formula in COP. COP is equal to refrigeration effect divided by refrigeration effect will also be equal to now Cp of T1 minus T4, not T4s. Okay, and work of compressor will be equal to H2 minus H1. Work of turbine will be equal to H3 minus H4 now. So you have to find the actual work of compression, actual work of turbine, and then you have to find the COP. Clear? Clear, everyone? So this is how you will be solving the questions. Okay, this is very important approach you have to remember. Next is psychrometry. Psychrometry is basically, it is that branch of science in which we study the properties of moist air. What is moist air? It is the sum of dry air plus water vapor. Degree of freedom of moist air is equal to 3. Degree of freedom of moist air is equal to 3. Okay, and psychrometric term, there are some important psychrometric terms that we study. That is, first is specific humidity. Okay, specific humidity is equal to mass of the vapor divided by mass of the dry air. Actually, it has to be mass of the vapor. Let us say we are having a mixture of water vapor and mixture of dry air. So actually the specific humidity should be the mass of the vapor in a mixture of moist air, But basically sometimes, as you know, that mass of the vapor is very small. Mass of the vapor is very, very small as compared to mass of dry air. So we neglect the mass of vapor in total mass. So we write that ratio as mass of the vapor divided by mass of the dry air. Yeah, that was for reverse Joule cycle, Shubham. Okay, so specific humidity is equal to mass of the vapor divided mass of the water vapor present in a mixture of moist air. But because in the moist air we are having very less amount of water vapor, so we'll be neglecting those water vapor and we'll be writing this as mass of water vapor divided by dry air. The unit of specific humidity is actually kg of water vapor divided by kg of dry air, or gram of water vapor per gram of dry air. But actually the unit is gram of water vapor divided by kg of dry air. Because water vapor has very less mass as compared to air. Water vapor mass is very, very small. Okay, but when in the exam they can ask you the question will be in kg per kg. They will give you the answer in kg per kg. When they will give you the specific humidity, they will give you that in kg per kg or gram per kg. Okay, so now you have to see the unit, in what unit they have asked the answer. If the answer is asked in gram per kg, then you have to find it in gram per kg. If it is asked in kg per kg, then you have to give in kg per kg. Okay. So specific humidity is equal to mass of vapor divided by mass of dry air. It is also equal to 0.622 of PV by P minus PV. Okay, this is also the formula of the, we can say that it is mass, specific humidity is equal to 0.622 of PV, that is partial pressure of the water vapor divided by total pressure minus partial pressure of the water vapor. So PV is the partial pressure of water vapor and it is also the saturation pressure. It is also the saturation pressure corresponding to dew point temperature. It is saturation pressure corresponding to dew point temperature, which is dPT. Saturation pressure corresponding to dew point temperature is also equal to PV. Okay, that is the formula. Again, P is the total pressure, total atmospheric pressure that will be given in the question. That will be atmospheric pressure that will be given in the question. Hi Bunny Kaushik, very good evening, welcome to the session. Relative humidity defines the moisture absorption capacity. It tells you what is the moisture absorption capacity. Moisture absorption capacity in the air. That is, it is a ratio of mass of water vapor in a normal condition, in unsaturated condition divided by mass of water vapor in the saturation condition. Saturation condition means it is that condition which tells you the maximum capability of the air to absorb moisture. That is called saturation condition. Okay. It is also equal to partial pressure of the water vapor divided by partial pressure of the vapor in saturation condition. This is the formula for the relative humidity is equal to PV by PVS. And PVS is corresponding to dry bulb temperature. Corresponding to dry bulb temperature, the saturation pressure will be equal to PVS. Okay, you have to remember that. And corresponding to dew point temperature, the saturation pressure will be PV. So we are having three temperature basically: dry bulb temperature, wet bulb temperature, and dew point temperature. Dry bulb temperature is the temperature of a normal air, which is measured by ordinary thermometer. Wet bulb temperature is a temperature which is measured by a same thermometer, but that bulb, the bulb of the thermometer, is covered by a wet cloth. The bulb of thermometer is covered by a wet cloth. That is called as and then it will give you the value of wet bulb temperature. So wet bulb temperature it indicates the moisture content in the air. The moisture content in the air is basically determine the amount of wet bulb temperature. It is also a very important temperature because it is the lowest temperature. It is lowest temperature achieved by evaporative cooling. The lowest temperature achieved by evaporative cooling is called as wet bulb temperature. Like in desert cooler and cooling tower. In desert cooler and cooling tower, the lowest temperature will be called as wet bulb temperature. So whenever you have this application of evaporative cooling or cooling and humidification, the lowest temperature that can be achieved up to which cooling can be produced is called as wet bulb temperature. Okay. Next is dew point temperature. It is that temperature at which condensation of the water vapor start to take place. At that temperature is called as dew point temperature. So for normal air or unsaturated air, the air which is not saturated, for that air, the dry bulb temperature is always greater than wet bulb and wet bulb is greater than dew point temperature. But for saturated air, the air which has got completely saturated with water vapor, in that situation, all these temperature becomes equal and relative humidity becomes 100% in that situation. That means the moisture absorption capacity is completely completed. Okay, clear? Next is the dew point temperature. Let me just come 1 second. Let me get my charger 1 second. Yes. Next important term is called as wet bulb depression. Wet bulb depression basically means difference. Difference of what? It is equal to difference of dry bulb temperature minus wet bulb temperature. It is called wet bulb depression. So desert coolers is a very important term called desert coolers. Desert coolers are more effective if wet bulb depression is high. If wet bulb depression is high, then desert cooler will be more effective. That is highest is the difference of dry bulb temperature minus wet bulb temperature, then desert coolers will be more effective. Okay. Please explain GSHF and RSHF also. Yeah, see GSHF and RSHF, I don't think that these question comes in your exam for GATE exam. That is important for your engineering services. But this load estimation is not important for your GATE exam. Okay. So I will only explain those things which are important for your GATE exam, not for engineering services. Dew point temperature, temperature corresponding to partial pressure of the water vapor. Although I have no problem explaining the RSHF and GSHF line, but it is not important for your GATE exam. Okay, it is important for engineering services exam, but we are not here studying for engineering services. We are here preparing for GATE exam. Degree of saturation is also called percentage humidity. It is equal to specific humidity for unsaturated air divided by specific humidity divided by for a saturated air. It is also equal to relative humidity PV by PVS into P minus PVS divided by P minus PV. This is a formula for degree of saturation or percentage humidity. Then enthalpy of moisture is equal to 1.005 into dry bulb temperature plus specific humidity into 2500 plus 1.88 into T. Or it is equal to enthalpy of dry air plus specific humidity times of enthalpy of water vapor. Enthalpy of water vapor is equal to 2500 plus 1.88 into T, that is dry bulb temperature. T here stands for dry bulb temperature in degrees Celsius and W is the specific humidity. Next, we are going to study about the psychrometric chart. There are different properties in psychrometric chart. Like constant dry bulb temperature in psychrometric chart are vertical lines like this. These are the vertical lines uniformly spaced, increase in this direction, they increase in this direction, and generally scaling of 5 degrees Celsius is provided. Constant specific humidity lines, these are the specific humidity. Here we represent constant specific humidity, here we represent dry bulb temperature. So these specific humidity will be increasing in the vertical direction, it will be decreasing in the downward direction. Okay. Then constant dew point temperature line. Dew point temperature are those lines which basically extend in this direction. And dew point temperature basically we measure on the saturation curve. Okay, here you measure the dew point temperature. Specific humidity you measure over here. You measure the specific humidity at this particular point on the wet bulb on the vertical axis. Then we have constant relative humidity lines. Relative humidity lines are basically the inclined lines. These are the curved lines like this, not inclined. These are the curved lines which are parallel to the saturation curve. This is the saturation curve. Saturation curve is basically that point where relative humidity becomes 100%. And the lines parallel to saturation curve are called as relative humidity lines. Relative humidity will increase in this direction and relative humidity will decrease in this direction. Okay. Then we have enthalpy, specific volume and wet bulb temperature lines. On a psychrometric chart, these two lines, enthalpy and wet bulb temperature lines, they have equal inclination. That is, the enthalpy and wet bulb temperature line, they will be shown by same line. Same line will be representing both enthalpy and wet bulb temperature lines. Only difference is that enthalpy will be having the unit of kilojoule per kg and wet bulb temperature will be in degrees Celsius. Enthalpy is shown outside psychrometric chart and wet bulb temperature on the psychrometric chart. Okay. One more important thing is specific volume has highest inclination. Highest inclination means the highest inclined line like this will be having highest inclination. These will be specific volume lines. So these three lines are inclined lines on the psychrometric chart. Okay. Now there are different psychrometric chart process like sensible heating. Sensible heating means increasing the dry bulb temperature. Increasing the dry bulb temperature at constant specific humidity. When specific humidity is constant and dew point temperature is also constant and we are increasing the dry bulb temperature, that is called as sensible heating process. Okay. So in sensible heating process, these two quantities will be constant. Enthalpy will increase, specific volume will increase, wet bulb temperature will increase, relative humidity will decrease. When you do this sensible heating, relative humidity will decrease. So hot air will be having less relative humidity. Always remember that. Sensible cooling will be having opposite effect. In sensible cooling will decrease the dry bulb temperature at constant specific humidity and dew point temperature. That is called as sensible cooling process. So this is what happens in the sensible cooling. But relative humidity increases. When you do cooling, relative humidity will increase. Okay. And all other parameters will decrease. Okay. Humidification is a process of increasing the specific humidity at constant dry bulb temperature. At constant dry bulb temperature, if you are increasing the specific humidity, that is called as humidification. Whenever you do the humidification, all the parameter will be except dry bulb temperature. Dry bulb temperature will be constant, except that all the parameters will be increasing. So specific humidity will increase, dew point temperature will increase, all the parameters will be increasing. So always remember that all parameters will increase. Dew point temperature is not related to human comfort. It is not the dew point temperature, Shubham. It is the effective temperature which is related to the human comfort. Okay. So that is the comfort conditioning, but that is not in the GATE syllabus. Comfort conditioning is in the engineering services syllabus. Okay. So it is the effective temperature which is required for the comfort conditioning, which basically determines the comfort of the human of different age groups or different basically male and female, children and aged people. Okay, so at what temperature they will feel comfortable, that is called effective temperature. But I just want to point out here that it is my request to everyone that please don't ask unrelated question in between the discussion, because we have to complete the revision of those topics which are important for GATE exam. Dehumidification is a process of decreasing the decreasing the dry bulb temperature, decreasing the specific humidity at constant dry bulb temperature. If dry bulb temperature is constant, we are decreasing the specific humidity, that is called as the dehumidification process, or it is the process of removing the moisture from the air. Okay, so in this, when you carry out the dehumidification process, all the temperature, all the parameters remains decreases. They decreases during dehumidification process. So in humidification, all the parameters will increase except dry bulb temperature, it will be constant. And in dehumidification process, you can also call it as dehumidification, also called as isothermal dehumidification. You can also call it as isothermal dehumidification because this dehumidification is carried out at constant temperature. Similarly, that humidification is also called as isothermal humidification. Isothermal humidification because it is carried out at constant temperature. At constant temperature, we are decreasing or increasing the humidity or moisture. If you want to represent all the psychrometric process on the single psychrometric chart, this is how you represent. So basically, this is humidification, this is dehumidification, this is sensible cooling, this is sensible heating. If you go in this line, this will be called as heating and humidification. So heating and humidification on a psychrometric chart will be represented like this, a line going like this. And in the line going like this, it will be called as sensible cooling and dehumidification. This is cooling and dehumidification. This is what happens in the air conditioner. In air conditioner, we have, in the air conditioner, in your AC, will be using the sensible cooling and dehumidification. Okay. Then we will be having this heating and this is the cooling and humidification. Cooling and humidification. Now this is a process which is used in the desert cooler. It is also called evaporative cooling. It is also called adiabatic humidification. Okay, and this is called as heating and dehumidification. So these are the four more processes which are very important on the psychrometric chart. Okay, clear everyone? Apparatus dew point. Apparatus dew point is basically the temperature. It is the temperature at which, when in the air conditioning, in air conditioning or air conditioner, as you know that we use the process of, cooling and dehumidification. So if cooling and dehumidification process is carried out in such a way that your cooling coil reaches the saturation curve. If your cooling coil temperature reaches the saturation curve, at that point what will happen? The condensation will take place from the coil. And at that point the temperature will be called as apparatus dew point temperature. Okay. So if you have noticed that when AC is operated in your house, okay, so sometimes some water start to drip out from your air conditioner. It will happen when your cooling coil temperature will reach the apparatus dew point temperature. At that point, this condensation of the water will start to take place from the cooling coil. And at that point, the temperature will be called apparatus dew point temperature. Then we have adiabatic humidification or saturation or chemical process or dehumidification. Now on this psychrometric chart, this line will be representing the adiabatic humidification, or it is also called as cooling and humidification. And this line going downward will be representing the chemical dehumidification or adiabatic dehumidification. Okay, it is also called as heating. This is also called as heating and dehumidification. So what is the meaning of adiabatic? Adiabatic means that when this process is taking place, there is no heat transfer taking place. That is called adiabatic. It takes place along constant enthalpy line. Along constant enthalpy line, if this process takes place, then that is called as adiabatic humidification, because at constant pressure, the heat transfer is equal to change in enthalpy. So if this change in enthalpy is equal to 0, then enthalpy will be constant. That is the meaning of that the adiabatic humidification and adiabatic dehumidification take place along constant enthalpy or constant wet bulb temperature line. So when you will be doing this process of adiabatic humidification, you will reach the wet bulb temperature. Okay. Next is adiabatic chemical dehumidification. In chemical dehumidification, we will be using some chemicals like silica gel alumina to absorb the moisture. Okay. So for that, then it is called as chemical dehumidification. So when we are using some chemicals like silica, gels, alumina, salt solution, something like that to absorb the moisture, that is called chemical dehumidification. Next important term is called bypass factor. Bypass factor basically tells you that in your heating and cooling coil, for example, the heating coil used in the application of heating, ventilation and air conditioning, that is HVAC, we use both the type of coil, heating coil and cooling coil. Also in the case of your comfort air conditioning, in summer and winter air conditioning, like in summer air conditioning, which is also called as cooling and dehumidification, in winter air conditioning, which is also called heating and humidification, we use different types of coil. We use heating coil and cooling coil. So what is the meaning of bypass factor? Bypass factor means the amount of air which has not contacted the coil and it has passed the coil. Without coming in contact with the coil, it has passed the coil. That is called bypass. That is called bypass air. And the bypass factor basically tells you the amount of bypass air. So let us say we are having a heating coil, it is having temperature of T3, this is temperature T1, this is temperature T2. So bypass factor of heating coil will be simply equal to, because it is a heating coil, the temperature T3 will be greater than T2 and T2 will be greater than T1. So in that case, bypass factor of heating coil, as you can see, bypass factor of heating coil will be equal to T3 minus T2 over T3 minus T1. This is how you will be finding the bypass factor of heating coil. We also have a term called contact factor or coil efficiency, which is equal to 1 minus bypass factor. Okay. Bypass factor of cooling coil. Cooling coil, if you are having a cooling coil will be used in air conditioner, as you know that. So if you are having cooling coil, it will be having temperature T3, this is T1. T1 is the temperature of the incoming air, this is T2. So you know that here T1 will be greater than T2, T2 will be greater than T3. So bypass factor of cooling coil will be equal to T2 minus T3 over T1 minus T3. This is the formula of bypass factor of cooling coil. And same here we'll be using the term called coil efficiency. Coil efficiency or contact factor will be equal to 1 minus bypass factor. Okay. Now the term called bypass factor of more than, if suppose that in the air conditioner, in the HVAC application, we are not using a single coil, we are using more than one coil. In that situation, what will be the bypass factor of more than one coil? So let us say we are having bypass factor of one coil, if it is equal to X, then bypass factor of n coil, if you are having n coils, then bypass factor of n coil will be equal to X power n. This is a very important approach, you have to remember that. Wet bulb temperature remains constant. Yes, wet bulb temperature and enthalpy both remains constant during adiabatic and humidification and dehumidification. Then there is a term called mixing of air stream, which is also important. Let us say we are having air 1, this is air 2. Okay, this concept is basically used in the basically when you study the load estimation in the psychrometric chart. I don't know that in the GATE exam, I don't think that the question comes from load estimation. Otherwise, I have definitely taught you the grand sensible heat factor and room sensible heat factor. I have no problem in teaching you that, but that question does not come in the exam. But mixing of air stream is important, because in grand sensible heat factor, when basically you combine the outdoor condition means, as you know that in your air conditioner, it is not that same air will be again used for cooling application. We'll be taking some amount of outside air or fresh air, and that fresh air will get mixed with the room air. So room air and the fresh air will get mixed, or we can say 20% of the fresh air, which is also called ventilation air, is basically mixed together, and that after mixing it is sent to the air conditioner for cooling application. So grand sensible means that some outside air will come here, and that outside air will be combined to the inlet conditions. Okay, and after combination with the inlet conditions, this outside air and the inlet air will basically combine here. So let us say this is the outside condition, this is the inlet condition. They will combine here, and at this point, after combination, let us say this is So there will be some outside air which will come here. Now that the outside air will be combined with the inlet air, and after combination this will be sent to the air conditioners. Okay, so the room sensible, basically if we join the room condition, if we join the room conditions, that is the room air inside the room with the condition of the air condition, that is called room sensible heat factor line. If we combine these inlet condition and outside condition combined together, and after combination if we combine them at this particular point, let us say they are combined to here. So after combination, let us say they are combined together at this particular point. This is the outdoor condition. Outdoor condition, that is some outside air has been taken, and this is the inside room air. So they will combine together at this point in the air conditioner, and then it will be sent to air conditioner. This line will be called as grand sensible heat factor line, and this line will be called as room sensible heat factor line. So room sensible heat factor and grand sensible heat factor are important. Room sensible heat factor is equal to room sensible heat divided by room sensible heat plus room latent heat. And grand sensible heat factor will be equal to, if we combine these two together like this, it will be equal to grand sensible heat divided by total heat. That will be called grand sensible heat. But basically the grand sensible heat basically combine the mixing condition, that is outside air and inside air mixed together, with the outlet condition of the AC. This is the outlet condition of air conditioner, supply condition, outlet or supply condition. That line is called grand sensible heat line. But this is not important for GATE exam. I want to tell you here is the mixing of air stream. Basic mixing is that we are having one air, let us say it is outside air, one is air is the inside air, they will mix together, and after mixing, let us say this is the final condition after mixing, or final state of air after mixing. Okay, clear? This is the final state of air after mixing. So let us say this is M1, H1, T1, W1. M1, this is M1 is the mass flow rate, H2 is the enthalpy, HS is the enthalpy, W is the specific humidity. So basically by concept of mixing, it is very simple. It is also called as mixing or adiabatic mixing. Adiabatic mixing, that is mixing with at constant enthalpy, adiabatic mixing. So basically here the total mass after mixing, the final mass after mixing M3 will be equal to M1 plus M2. And this is by mass conservation. By energy conservation, we can say that M1H1 plus M2H2 will be equal to M3H3. Okay. M1W1 will be plus M2W2 will be equal to M3W3, and M1T1 plus M2T2 is equal to M3T3. So this is our important equation for mixing. Okay. So from here you can find the value of H3. It is equal to M1H1 plus M2H2 divided by M1 plus M2. If you have to find the value of enthalpy after mixing, if you have to find the value of specific humidity after mixing, this will be M1W1 plus M2W2 over M1W1, M1 plus M2. So in this way we can find the value of enthalpy or specific humidity after mixing. Okay. Now there are some important notes that is important. Cooling and dehumidification is only possible when cooling coil temperature is less than dew point temperature. During heating and dehumidification, the dry bulb temperature increases and specific humidity will decrease. Example of heating and humidification is steam spray in the air. In case of desert cooler, we achieve cooling and humidification. Desert cooler are more effective when wet bulb depression are high. These are some important points. Ventilation air means fresh air. Generally, basically, human feel comfort at 24 to 26 degree dry bulb temperature and 50-60% relative humidity. These are the comfort conditions. Ventilation air is the fresh air that is supplied for the air conditioning equipment in order to maintain its purity. That is called ventilation air. Okay, in operation theater we require 100% fresh air. In summer air conditioning we use cooling and dehumidification. In winter air conditioning we use heating and humidification. These are some important points. It is not in the syllabus, Amit Yadav. Forget about the grand sensible heat factor. I was just telling you, one of the students who was asking me. I think Saeed Akhtar was asking about the grand sensible heat factor, but it is not in the syllabus. Although I told you about that, it is not in your syllabus. Okay. Now let us solve some questions quickly. Hurry up. We don't have much time. It is 8:30. In next 45 minutes we'll be solving 15 questions. So hurry up, guys. I will not give you much time for solving the questions. Yes, hurry up. Be quick. Come on, tell me everyone. Tell me the answer for this question. Hurry up, be quick. Yes, tell me what is the answer for this question. A process changes the initial state of air from 30 degrees Celsius dry bulb temperature and 58% relative humidity. So as you can say that dry bulb temperature is getting dry bulb temperature is getting increased and relative humidity is getting decreased, right? So this process is basically only possible in one condition. Yes, and that condition is, tell me, when is this possible that relative humidity is getting decreased and dry bulb temperature is getting increased? It is only possible in the case when heating and humidification take place. Sorry, heating and dehumidification take place. That means in this situation, let us say this is at 30 degrees Celsius. At this condition, the relative humidity, let us say, is 58%, let's say. And in this situation, the relative humidity is 20%. Okay, so this is possible only in heating and dehumidification. So the answer will be option C for this question. Clear? Clear everyone? The answer will be option C for this question. Next question. A refrigerator working on an ideal vapor compression cycle uses R134 as its refrigerant. The refrigerant vapor enters into the compression at minus 10 degrees Celsius at enthalpy of 402 and leaves the compression at 50 degrees Celsius at enthalpy of 432. So for solving the question, it will be better if you draw the diagram of a vapor compression cycle on a pressure enthalpy diagram. So this is at point 1, this is at entry, this is 402, this is 432. Okay. You have to find the enthalpy leaving the country. You have to find the value of H3. How can you find the value of H3? COP is equal to 5.5 in this question. Yes, come on everyone, tell me the answer. Yes, very good. Everyone has given option C for the last question. Good, very good. It is heating and dehumidification. Now tell me the answer for this question. Today the response is very bad. I don't know why. When we provide you this session, then some of the students basically in the first session they were around 50-60 students. Then after that in the second session, third session, then the student also were like 40-50. Now I can see that the number of students are continuously decreasing. Why? Because now you know that I will provide you this session. So it is basically a simple saying that some people say that that when you get something you don't take you don't feel the importance of that thing. The importance of that thing decreases. That is a simple meaning that I can see from here. That now the strength of the class is decreasing at such a alarming rate. That is actually very alarming. That why the strength is decreasing. Hi Kuldeep Datta, very good evening. Welcome to the session. Come on, tell me what is the value of H3 enthalpy leaving the condenser you have to find. Very simple question. Saeed Akhtar has got 237. Those who have joined me for the session also please give some time to like the session. COP is equal to H1 minus C. Normally we know that it is equal to H1 minus H4, but we can also write it as H1 minus H3 by H2 minus H1 because we know that H3 is equal to H4. So everything is given. The answer will be what? 237. Yes, it is 5.5 is equal to H1 which is 402 minus H3 divided by 30. H3 will be equal to 237. It is a simple question. It is a very simple question that can be asked in GATE exam. Next question. In a cascade refrigeration cycle, two refrigerators is working in series with COP 5 and 3. If this refrigerator is running by a Carnot engine having temperature limit 600 Kelvin and 300 Kelvin and heat supply to Carnot engine is 2 kilowatt, then COP of Cascade Refrigeration is 1.67. Refrigeration effect is 1.67. COP of Cascade Refrigeration is 1.4 or refrigeration effect is 2.34. What will be the answer for this question? Hurry up. Hurry up guys, come on, tell me quickly. Tapan has, yeah, Tapan, Akash, Deepak, Shivani, Arun, Saeed Akhtar, your answer was correct, very good. Now tell me the answer for this question. Come on everyone. We are having a cascade refrigeration cycle. And COP of cascade is, as you know that, COP of cascade refrigeration is equal to COP of the first cycle into 2 second cycle divided by 1 plus COP of the first cycle plus COP of the second cycle. This is the formula. Now COP is given here of both the cycle. It is simply equal to 5 into 3 divided by 1 plus 5 plus 3. It is a very simple question. Yes, come on. Hi Manish, very good evening. Welcome to the session. Yes, one answer is 100% correct. That is 1.67. COP of cascade will be 1.67. What about the other part? Refrigeration effect is 1.67 or 2.34? Yes, come on, tell me, everyone. Hurry up. Now we are having a Carnot engine. The heat supplied is given. Efficiency of the Carnot engine, as you know that, efficiency of the Carnot engine will be equal to 1 minus 300 by 600. Efficiency will be 0.5 and that will be equal to work done by heat supplied. So work of Carnot engine will be equal to 0.5 into 2, which will be 1 kilowatt. Now this 1 kilowatt work will be given to what? It will be given to this cascade refrigeration cycle. Okay, so COP of this cascade refrigeration is equal to 1.67. That will be refrigeration effect divided by work input. So work input is equal to what? 1. So you will be getting refrigeration effect is equal to 1.67. So the answer will be option A and B. Simple question, very simple question. Clear everyone? Is it clear to all of you? I hope you are not having any doubt. Sarat Lal has given right answer, Arun has given right answer, Shubham has given right answer. And those who are not able to give the right answer, you have to really see this, how you are getting the wrong answer. Okay, next question. Which of the following are true for application of refrigerants? Which are the true for the application of refrigerant? Ammonia used with reciprocating and screw compressor in the cold storage ice plant food refrigeration. Water is used in water lithium bromide absorption system and ammonia in aqua ammonia system. Okay. Carbon dioxide used as solid carbon dioxide or dry ice in frozen food transformation. And the last statement is refrigerant 11, R11 or CFC11 used with reciprocating compressor in the small units, especially domestic refrigerator water cooler. Hurry up guys, hurry up, be quick. I have to solve 15 questions. I will not give you more than 9:15. 9:15 is the last question I will be taking today because I cannot extend the session. So you have to match your target that you have got only that much time. So the right answer will be option A is correct. Option B is correct. Option C is correct, but this is not correct. With reciprocating compressor, we don't use R11. We use with reciprocating compressor, either we use R11 or basically we use R22 in domestic refrigerator water cooler, or we use R12 as a refrigerant. We use R12. R11 is used for central air conditioning. Central air conditioning. In central air conditioning, we use R11. First of all, R11 is used for centrifugal compressor. It is used with centrifugal compressor, not with axial reciprocating compressor. R11 used with centrifugal, not axial reciprocating. Reciprocating compressor are used with ammonia and carbon dioxide. Okay, because R11 refrigerant is used for large refrigeration, like central air conditioning. Okay, it is not used for small units like domestic refrigerator water cooler. Next question, a vapor compression refrigeration uses R40 and operates between temperature limits of -10 and 45. At the entry to the, this is 45 degrees Celsius. At entry to the compressor, the refrigerant is dry saturated. This is question number 3. Hurry up. At the entry to the compressor, the refrigerant is dry saturated, and after compression, it requires a temperature of 60 degrees Celsius. Relevant properties are given in this table. You can see this table is given here. You have to tell which of the following statement is correct. Yes, come on, hurry up, guys. And my dear, if anyone has joined the session now recently, then please also give some time to like the session and share the session. Come on, tell me everyone, what is the answer? How can you solve this question? We are having a vapor compression system using R40 as a refrigerant, operating between these two temperature limits of -10 and 45. You have to tell what is the COP. They have given everything. At -10 temperature, they have given enthalpy of the liquid. Let me just write it. Maybe it is blood. Slowly explain kariye. Hi Kuldeep. Basically, I don't have much time to explain this slowly because I have to cover a lot of things. Okay. So it is a revision session, my dear. And in revision session for GATE exam, I cannot become that. My speed is, I think, same for a revision session. Yes, come on everyone, tell me the answer. How can you solve this question? I hope the table is clearly visible to you all. At -10, the value of enthalpy of the liquid is 45.4. And if I will go slow, then we won't be able to cover 15 questions. Maximum 7 questions we will be. Okay, Sarat Lal has given A and D. Yes, A is correct and D is correct. Very good. Let's see the solution of this question. See, I cannot explain the solution in this page, so I have to move to the next page. So for seeing the solution of this question, let me draw the diagram first. Okay, so diagram will be actually like this. Because it is a vapor compression cycle, this is 1, this is 2. This is 3, this is 4. Okay, my dear. So how to solve this question is very simple. Now we have to find the COP. COP will be equal to what? It will be H2 minus, H1 minus H4 divided by H2 minus H1. H1 will be the enthalpy at this temperature, at -10. At -10 degrees Celsius. Another temperature is given as 45. This is 45, right? So at -10 degrees Celsius, the enthalpy of the liquid vapor at -10, this will be the value of H1, right? Clear? The answer will be A and D. Very good. So this will be the H1 is equal to what? H1 will be equal to 460.7. Similarly, at 0.3, at 45, for 45 degrees Celsius, this will be the enthalpy of liquid, that is 133. This will be H3 will be equal to 133. You only require the value of H2. How can you find H2? How can you find the value of H3, H2? It is very simple. We know that S1 will be equal to S2 because 1 to 2 is an isentropic process, right? Entropy at point 1 is given. Entropy at point 1 will be this 1.637. So this is 1.637. Entropy at point 2 at this particular point will be equal to what? This is the entropy in the superheated region. I told you that entropy in the superheated region is equal to entropy at this particular point, this, plus Cp of log of T2 by T saturation. I hope you remember this formula, right? So we will be using this formula. You know the value of T2. Do you know the value of the superheated temperature? The temperature after superheating. The temperature after superheating, after compression, the temperature is 60. That means this temperature is 60 degrees Celsius and this temperature is 45 degrees Celsius. So this will be equal to Sg. This is value of Sg. So this will be 1.587 plus Cp of vapor. Cp of vapor is given in this question or not? Cp of the vapor is not given, I think. No problem, Cp of vapor can be found from here. Cp of vapor can be found. Cp of vapor log of T2. T2 will be equal to what? T2 will be 60 plus 273 and T1 will be equal to 45 plus 273. So from here you will be getting the Cp of vapor. You just equate this S2 with S1. Okay, that is 1.587 plus Cp of vapor log of 60 plus 273 divided by 45 plus 273. You will find Cp which will be equal to Cp of vapor which will be equal to 1.085. Now you know that H2 minus Hg will be equal to Cp of vapor of T2 minus T saturation. That means this H2 will be equal to Hg. Hg is equal to how much? This is the value of Hg. 483.6. 483.6 plus 1.085 into T2, that is 60 minus 45. From here you will be getting this value H2. This is 499.87. Are you getting this value of 499.87? Now you have got H2. You know value of H1, H4. H4 is equal to H3. So COP will be equal to 460.7 minus 133 divided by 499.87 minus 460.7. So you will be getting the answer. The answer will be equal to 8.365. Are you getting the answer, everyone? Tell me. Is everyone getting the answer? Please. This question can be asked in 2 marks in the GATE exam. 100%. Okay. In MSQ question, this question can be asked. Next question. Question number 4. Question number 4, hurry up. A VCR system uses refrigerant R134 and operates between 0.15 megapascal and 80 kilopascal. If the value of the enthalpy at entry and exit of evaporator are 78 and 178 and enthalpy at the inlet to the condenser is 220, if the power supplied to compressor is 4.2 kilowatt, then yes, tell me everyone, what is the answer? Hurry up guys, hurry up. We are having a VCR system using refrigerant R134 and operates between temperature of, so basically we are having a VCR system. So you can plot this like this. Okay. Now you can draw the diagram. Okay. So I'm just going very slowly so that you can understand it. Now we are having the enthalpies given here. The enthalpy at the inlet and exit are given. So this is 78, this is 178. Okay. And the enthalpy at the inlet to condenser, this is 220. Clear everyone? You have to tell which of the following option is correct. Yes. So refrigeration capacity is 10 kilowatt or mass flow rate is 1.1, COP is 2.38 or COP is 1.96. Which of the following option is correct? So you know that COP will be equal to what? H1 minus H4 divided by H2 minus H1. So first thing, go for the COP. It will be simply equal to 178 minus 78 divided by 220 minus 178. You will be getting the COP. COP will be getting how much? Yes, are you getting the cell COP everyone? COP will be getting equal to 2.38. So option C is 100% correct. What about the other options? You know that power supplied is given 4.2. Power is equal to mass flow rate into H2 minus H1. Right? So 4.2 will be equal to mass flow rate into H2 minus H1, which is 220 minus 178. So from here you can get the mass flow rate, which will be 0.1 kg per second. And refrigeration capacity is equal to mass flow rate into H1 minus H4, which will be 0.1 into 100. This will give you 10 kilowatt. So option A, B and C all are correct. Very good. Those who again option A, B and C. Good. Very good. So this is how the MSc question can come in the exam. Okay. This is just an idea to tell you how the MSc question can come in GATE exam. Next question. The enthalpy at various points in the VCR cycle are given. This type of question can come in 1 marks. This type of question can come in 1 marks in the GATE exam. Enthalpy at various points are given. You have to tell what is the value of refrigeration effect, work input, COP, what is correct. Hurry up, come on everyone, hurry up. Yes, hurry up guys, please. What will be the right answer for this question? Again, a very simple question. Very simple question. They have given the enthalpies at all the points. Enthalpy at inlet to compressor, that is H1 is given. Inlet to evaporator, that is H3, H4 is given, and H2 is given. All the enthalpies are given. A very simple question. This type of question can be asked in 1 mark. This is question number 5. Hurry up. Hurry up, come on guys, hurry up. Very simple. Refrigeration effect is equal to what? Refrigeration effect is H1 minus H4. A question cannot be simple than this type of question. It is the simplest question can be asked in GATE exam in 1 marks as MSQ type question. Okay. So tell me what will be the answer. It is H1 minus H4. H1 is equal to 100 minus H3. This is 40. So that means option C is correct. Work input will be equal to what? H2 minus H1. That will give you 20. This is option B is correct. And obviously this is option C. This is COP will be equal to 40 by 20. This will be 2. Very simple question. Very simple question. But this type of question can be asked in 1 marks. They can give you the value of enthalpy. They can ask you to find directly the value of refrigeration effect, work input, COP. 1 mark MSQ question will be like this. Okay. In numerical. Very good. Everyone has given the right answer. Good. Next question. Ambient air at 35 degrees Celsius, 75% relative humidity, and at standard atmospheric pressure. At 35 degrees Celsius, saturation pressure is given. That is 35 degrees Celsius is PVS is given, which is 0.05628. I have told you that corresponding to dry bulb temperature, the saturation pressure is equal to PVS, and corresponding to dew point temperature, the saturation pressure is PV. So you have to tell which of the following option is correct. Good. Jaldi answer dijiye. Come on, everyone. Big quick guys, hurry up. Which of the following option is correct? We have only got 20 minutes. Only 20 minutes left for the session. So we have to really increase our speed. This is question number 6. Ambient air at 35 degrees Celsius, 75% relative humidity. Very simple question. They have given the relative humidity, which is 0.75. It is equal to PV by PVS. Question can be more easy than this type of question? Yes. They have asked the partial pressure of water vapor, that is PV. They have asked the specific humidity. Very simple question. The atmospheric pressure. The standard atmospheric pressure is equal to what? The standard atmospheric pressure is not given. It is, you can take it as 1 bar if it is not given. sorry, one atmospheric pressure is not 1 bar, you can take it as 1.0325 bar. That is approximately, that is 1.0325 bar. Approximately it is 1 bar. Okay. So if it is not given, you have to remember that at standard atmospheric pressure is equal to 1.0325 bar. Yes, what will be the answer for this question? So yes, A and B will be the right answer. Very good. You will be getting PV will be equal to 0.75 into 0.05628. Okay, which will give you 0.04221 bar, and specific humidity is equal to 0.622 of PV by P minus PV, which is simply equal to 0.622 of PV is equal to what? PV is given in this question, which is you have just found PV 0.0422 divided by 1.01325. ठीक है, minus 0.0422. You will be getting this value as 0.027. Are you getting this value, everyone? Yes. Next question. A heating coil has bypass factor of 0.6 and surface temperature of 50. This is question number 7. Hurry up. We are having a heating coil having bypass factor of 0.6 and surface temperature of 50. If similar 4 heating coils are placed inside a duct in series, and the moist air of dry bulb temperature 25 is sent at the inlet of the duct. Yes. Thank you, Shubham. I hope you guys are enjoying this session, because if you guys are enjoying this session, then that is the best thing that I can achieve, and best what you can achieve is you can learn the concept, you can practice the concept live here. And what I can basically feel is that I am getting connected with you guys. That is, Keshav, my dear, power plant will be tomorrow. Okay, tomorrow the last day of the year. Power plant I will teach you in the last day of the year. Okay, heating coil is a bypass factor. We are having a bypass factor of 1 coil. 1 coil is equal to 0.6. We are having 4 heating coil. So bypass factor of 4 coil will be equal to 0.6 power 4, right? So you can simply say 0.6 power 4 will be equal to what? 0.1296 equal to 0.13 approximately. So A is correct, 100%. Now all these 4 coil combined together. Let us say this is a common coil combined together. So inlet temperature of this is equal to 25. This coil temperature is equal to 50 degrees Celsius. Combined temperature is 50. Outlet temperature you have to find. That is simply equal to the bypass factor will be equal to T3 minus T2 divided by T3 minus T1, which is 50 minus T2 divided by 50 minus 25. Okay, clear? So you can say this will be 0.13. So you will be getting T2 is equal to, T2 you will be getting as 46.75 degrees Celsius. So option A and B will be correct. VLSI MTech, how much rank? Ananya Roy, actually I am not from computer science background, dear. So I can't, I won't be able to tell you that I am not from computer science or electrical. So it won't be possible for me to tell you about that. Okay, or we can say that I am not the right person to tell you about this, because I am from mechanical background actually. But if you want to pursue MTech, how much rank you require, whether you're from electrical branch or you're from mechanical, any branch, it depends on from which college you want to pursue your masters. Question number 8. It depends on which college you want to pursue your master. If you want to pursue college from IT or NITs, then you require at least a rank below 2000. Okay, below 2000 rank or below 2500 rank is required for masters. Okay, and if you want to pursue your master from, I think nobody wants to pursue master from any other colleges except IT and NIT. So you should aim for below 2000 rank. Consider the following property: degree of saturation, specific humidity, humidity ratio, relative humidity. Which of the following have the same meaning? The answer will be option B and option C. A and B, degree of saturation and specific humidity, they are same. Degree of saturation, how they are same? It is equal to W by Ws. Specific humidity is equal to mass of the vapor divided by mass of the air. Actually, specific humidity and humidity ratio both are same thing. So the answer will be option B and C for this question. The right answer will be option B and C. Next question, question number 9. The process of sensible heating increases specific enthalpy, decreases specific humidity, decreases relative humidity, or increases relative humidity. Come on everyone, tell me the answer quickly, be quick. Process of sensible heating. Sensible heating will do what? Sensible heating is a process. There are many chances of placement. The chances of placement are good in the IITs from VLSI branch, VLSI specialization. Okay. So what will happen? Relative humidity will decrease in sensible heating. What will happen to specific humidity? Yes, specific humidity will decrease or increase. The answer will be only option C for this question. Okay, clear everyone? So the answer will be option C for this question. Only C. It will, specific humidity will be constant. Specific humidity will be constant. It is not A and C. Now option A, yeah, option A is specific enthalpy. Okay, yeah. So if you talk about enthalpy, if you talk about enthalpy will increase in this direction. So yes, option A will also be correct. I have not read the option. Your answer is correct. Sarat Lal, your answer is absolutely correct. So it's actually option A and C. If you read option A, specific enthalpy will increase if you go from in this direction. Okay? Yeah, specific enthalpy will increase. It is specific enthalpy, my dear. Okay? Question number 10. During evaporative cooling process, so this type of theory question can be asked in the exam as MSQ questions. This type of theory question can be asked in MSQ question. During evaporative cooling process, cooling and humidification take place. Wet bulb temperature remains constant. Specific enthalpy remains constant. Relative humidity will decrease. Evaporative cooling process, I told you that it is represented by a line like this. This is how the evaporative cooling is represented. So during evaporative cooling, it is also called cooling and humidification. That is correct. Wet bulb temperature remains constant. That is also correct. Enthalpy remains constant. That is also correct. Okay. Hi Saeed Akhtar. I think that you are preparing for GATE exam, my dear. And you should know that from GATE 2021, only from GATE 2021, they have introduced the MSQ type questions. So yes, because they have especially mentioned that they will be asking MSQ questions. That is the reason that I am providing these questions. Okay. What about relative humidity? Relative humidity will increase or decrease? Relative humidity will obviously increase. So option D is also correct. Okay, so all the options are correct. Next question, question number 11. Hurry up guys, hurry up, be quick. The statement concerns psychrometric chart. Which of the following statements are correct? Constant relative humidity lines are uphill straight lines to the right. Constant wet bulb temperature lines are downhill straight line to the right. Constant specific lines are downhill straight line to the right. Or constant enthalpy lines are coincident with constant wet bulb temperature lines. So one option I can easily say D is correct. Just by looking the option, D is correct. Constant enthalpy lines are coincident with constant wet bulb temperature lines. Constant specific volume side lines are downhill straight line. Downhill straight lines? No. Specific volumes lines are not first of all downhill. Downhill straight line, they are not like this, they are like this. Constant specific volume lines, constant wet bulb temperature line are downhill straight line to the right. So yes, this is how the constant wet bulb temperature lines are. They are the constant lines going to the towards the right, constant lines going downhill to the right side. So B is also correct. Constant relative humidity lines are uphill straight line. No, this is not correct. Constant specific volume lines are downhill straight line to the right. Actually, this is, yeah, they will be also like this. Specific volume lines are also like this. They are also toward the right. Also, we can say that. But what is the meaning of downhill? Downhill means climbing a hill. If you go on the hill like this is the uphill. Uphill. Downhill means this. This is the downhill. Downhill means going down the lines. Clear, everyone? So which option is correct here? Tell me. Which option will be 100% correct? Is option C correct or not? Constant specific volume lines are downhill straight line to the right or not? Like constant specific volume wet bulb temperature lines are downhill straight line. They are downhill and they are towards the right. They are also towards the right, but they have more slope, more inclination. So option B, C, D are correct here. Next question, question number 12. Moist air of dry bulb temperature 27 and relative humidity of 70% have total pressure of 95 kilopascal. Saturation pressure of water at 27 is 3.57. Sorry, why they have written water? Moist air, you can say moist air. So they have given the value of PVS in this question 3.57 kilopascal. They have given the total atmospheric pressure as 95 kilopascal. They have given the relative humidity as 70%. You have to tell what is the right answer. Right and left का क्या मतलब है? अरे A is not correct, सही अक्तर my dear. Constant relative humidity lines are uphill straight line. They are not uphill, they are सही अक्तर my dear. Have you seen the relative humidity lines are straight lines? They are curved lines. They are not straight. Okay, they are not straight lines. They are curved lines. So A is not correct. Question number 12. Moist air of dry bulb temperature 27 degrees Celsius and relative humidity of 70%, having total pressure of 95. What is degree of saturation? Degree of saturation is equal to relative humidity into P minus PVS over P minus PV. It's a very simple question. You have to find the value of PV first. PV will be equal to relative humidity is equal to PV by PVS. Okay, so PV will be equal to 0.7 into 3.57. We'll be getting the value of PV. Are you getting the answer, everyone? Yes. So you can find this value. This will be 2.5 kilopascal. So A is correct for this question. What about the second option? Degree of saturation. Degree of saturation will be 0.69 or 0.72. So if you solve this, you will be getting 0.7 into 95 minus 3.57 divided by 95 minus 2.5. Solve it, you will be getting the answer as 0.692. So option A and B are correct. Very good, everyone. Arun, Sarath and Akash. Good. Next question, question number 13. Air at 20 degrees Celsius dry bulb temperature and 75% relative humidity is sensibly heated until its temperature becomes 25. The saturation pressure at 20 and 25 are given. The mass flow rate of air is also given. Atmospheric pressure is given. You have to tell what is the specific humidity of air and what is the heat added to the air. Now this is a very good question. I can consider this a very good question. And also We are running out of time, so I will be completing the session very soon. Okay, so hurry up guys. Hurry up, come on, be quick. Air at 20 degrees Celsius dry bulb temperature and 75% relative humidity is sensibly heated until its temperature becomes 25 degrees Celsius. Sensibly heated, sensible heating is taking place. So if you have to draw the diagram will be like this. So we are having a air which is getting heated from 20, let us say this is 20, let us say this is 25, let's say 25. Sensible heating means specific humidity will be constant. So whatever will be the specific humidity at this point, at let's say this is 0.1, this is 0.2. Whatever will be the specific humidity at this point, same will be at this point. So W1 will be W2. You have to find the specific humidity of the air. They have also given that at 20 degrees Celsius, the partial pressure is given that at 20 degrees Celsius, the relative humidity is equal to 75% and partial pressure is given 2.01 kilopascal. So it is very obvious that specific humidity, relative humidity is equal to PV by PVS. That will be equal to 0.75 is equal to PV by PVS. PVS is equal to how much? This is 2.01. So PV will be getting from here. What will the value of PV? Tell me. PV will be equal to 1.5075. 1.5075 will be the value of PV from here. So you have got the value of PV. Now my dear, so Akash has given option A, D, Sarath Lal, A, D, A and D. Yes, absolutely correct. A and D is the right answer. Good. Let's see the solution. So this is PV. So specific humidity you can find at 0.1, which will be 0.622 of PV over P minus PV. The atmospheric pressure is 1.013 bar. So it will be equal to 101.3 kilopascal. That will be 0.622 of PV. PV is equal to 1.5075 divided by 101.3 minus 1.5075. You will be getting the specific unit which will be 0.009396 kg per kg. Now whatever will be the value of specific humidity at 0.1, same will be at 0.2 because it is constant. So the answer is option A. What about the heat added? Heat added will be equal to mass flow rate into H1 minus H2. Because enthalpy has increased. When sensible heating takes place, enthalpy will be increasing from H1 to H2. Enthalpy at 0.1 will be equal to 1.005 into dry bulb temperature at 0.1 plus specific humidity at 0.1, 2500 plus 1.88 into dry bulb temperature at 0.1. At 0.1 dry bulb temperature is 20 degrees Celsius. So corresponding to 20 you will be finding the value of H1, right? So H1 will be equal to 43.94. Are you getting this 43.94? Okay, kilojoule per kg. And H2 will be equal to what? H2 will be finding at this point, let us say, where should I write? H2 is equal to, same way, it is 1.005 into 25 plus specific unit is 0.00, because specific unit is 0.12 is same, 0.009396 into 2500 plus 1.88 into 25. So you will be getting value of H2. H2 will be getting as 49.06. Are you getting this value of kilojoule per kg? If you multiply this, you will be getting mass heat will be 15.36 kilowatt. Mass flow rate is given in the question 3 kg per second. Clear everyone? Is this question clear to everyone? This is a very important question. Very important question. Okay. Question number 14. Hurry up. Second last question. Second last question. Hurry up. Hurry up. Air at 25 degrees Celsius is mixed adiabatically with air at 45 in the ratio of 2 kg of former with 3 kg of later. So we are having one air at 2 kg, which is at 25 degrees Celsius, and we have 1 kg air is 3 kg, which is at 45 degrees Celsius. They are mixed together, and after mixing they will be supplied at this point 3. Okay, clear everyone? I think some of the students wants to have their dinner, that is why they have left the session. See, this thing I am not able to understand, why the students are not that much focused. Why some people think that we are providing this session for something for ourselves? No. We are providing this session for you so that you can clear the GATE exam. If I can speak from 7 p.m. to 9:15 p.m. and I can sit like that, then why can't you just, who have to actually give the GATE exam, why can't you can basically present in the session? Because I have seen that sometimes the students are 30, 35, 40, then some students leave the session. Why? Because you want to look for your comfort. Okay, I will watch the recorded session. It is good. You can do that thing. But when you are coming to the session, then see the live session, right? It is much useful to see the live session. Final humidity will be equal to, humidity ratio means specific humidity. So it will be equal to M1 W1 plus M2 W2 divided by M1 plus M2. So everything is given. The specific humidity is given at point 1 and 2. Just put the value. So W1 is given, W2 is given. You will be getting this value as 3. Yes, what is the answer you will be getting? 3.632. You will be getting 3.632. Firstly, you will be getting that value in kg per kg. Then you have to multiply with 1000. That will give you gram per kg. You have to see the unit also. So you will be getting this value as 3.632 kg into 10 to the power minus 3 kg per kg. Because you have to find in gram per kg, you have to multiply with 1000. So it will be getting this value. And the total enthalpy will be equal to M1H1 plus M2H2 divided by M1 plus M2. Everything is given. H1, H2 is given. H1 is given. Just put the value, will be getting 72.2. Okay? Clear? Next question, last question, question number 15. An air refrigeration cycle working on reverse Brayton cycle. I know that some of the students are very diligent and you are all are very hardworking. You know that, because see, I am saying this point, but it is very obvious that especially for those students who have joined the session and then left afterwards, if you guys cannot give 2.5 hours or 2 hours of your time for your exam, for your results, then my dear, I think you are not serious for the exam. That is the simple meaning of that. Because I am serious that I want you to crack the exam, but I think you are not serious. An air refrigeration cycle working on reverse Brayton cycle inputs air at 7 degrees Celsius and 4 bar and reject the heat at 37 and 16 bar. Okay. The isentropic efficiency is also given for compression and turbine. You have to find the refrigeration effect, COP and all. So basically we are having a reverse Brayton cycle. Okay, they have given the isentropic efficiency. Didn't I tell you the concept of isentropic efficiency? Same concept will be used. 1, 2, 3, 4. This is 4 dash 2s 2. So you have to find the refrigeration effect. Refrigeration effect will be equal to Cp of T1 minus T4. T1 is given. T1 is 7 degrees Celsius. That is 280 Kelvin. Okay. Now COP you can easily find. COP is equal to 1. No, COP you cannot find by direct formula. Can you use this formula, my dear? Can anyone tell me? No, you cannot use this formula because they have given the isentropic efficiency. So you cannot use this formula for COP. Okay. So COP will be equal to what? COP will be equal to refrigeration effect divided by work of compression minus turbine. Compressor work will be equal to Cp of T1 minus T2 minus T1. This T2, not this T2. And this turbine work will be equal to Cp of T3 minus T4. This T4, not this T4. So you know that T2 by T1 will be equal to pressure ratio of gamma minus 1 by gamma. So T2 will be equal by 280 will be equal to pressure ratio will be 4. This is 4 bar by 416. This will be 4. P2 by P1 will be equal to what? 16 by 4. That will be 4 bar. 4 power 0.2857 because gamma will be taken as 1.4. So T2 will be getting from here. What will the value of T2? Tell me. T2 will be equal to 416. But this is not T2. This is T2S. Isentropic temperature. This is 416. 416 Kelvin. Okay. Now it is very obvious that isentropic efficiency of compressor is equal to T2 isentropic T2S minus T1 divided by T2 minus T1. This is equal to 0.8 is equal to T2S, which is 416 minus 280 divided by T2 minus 280. You will be getting the value of T2 from here. What is the value of T2? Yes, many of the students have got AB. Taran Papan has got AB for this question. Sarat Lal B. So the right answer will be AB for this question. Very good. A and B will be correct. Good. So T2 will be getting from here. T2 will come out to be how much? So T2 will be 450 Kelvin. Now next thing is you have to find the value of, because you have got T2. You have to, you know that T2 by T1, T2S by T1 will be equal to T3 by T4S, isentropic. T3 is given 37 degrees Celsius. T3 is 37 degrees Celsius. Okay, it is 310 Kelvin. So this is 310. T2S you have already found 416. You will get the value of T4S from here. T4S will be equal to how much? 208.6 Kelvin. And finally you will be using this formula. That isentropic efficiency of turbine is equal to T3 minus T4 divided by T3 minus T4S. You know T3, you know this efficiency is 0.85. Okay, if you put all the values T3, 310 minus T4 divided by 310 minus 280, 208.6. So you will be getting the value of T4 from here. T4 will be equal to how much? T4, actual T4 will come out to be, yes. What is the value of T4 you will be getting from here? Tell me. T4, tell me. $223.81. Okay. So you just get all the values. Okay. And you just put all the values here. You will be getting CP. CP will be taken as 1.005 if not given. Okay. So you will get the compressor work, you will be getting turbine work. You will find the refrigeration effect from here. Cp of T1 minus T4. This T4 you have to put. This T4, this T2, T3 and T1. These temperature you have to put, you will be getting the COP as 0.67. Clear? Are you getting this answer? Everyone? Put all the values, you will be getting COP as, COP will be equal to, this formula will not be used. You will be getting using this formula. COP will be equal to refrigeration effect divided by work of compressor minus work of turbine. This formula will be used for finding the COP. Okay. So you will be getting the answer from there. You will be getting 0.67. Are you getting this point, everyone? Everyone, please tell me. So this is the last question, and with this I would like to conclude the session. And guys, if you want, you can also tomorrow will be the last session of revision session. Tomorrow will be the session for power plant subject. Okay, so tomorrow we'll be revising the power plant subject, and with this also will be solving the question. So no matter whether students come in the session or not, tomorrow is 31st of December. I know tomorrow you must, some of you think that we'll celebrate New Year. Who don't want to celebrate New Year? I also want to celebrate New Year, but although I'm employed at GradeUp, I know that I have to teach you because I have to take the lecture. But tell me very frankly, is I will be getting salary from GradeUp, that is another thing. But it is you who has to give the GATE exam. If I can take out time to take lecture on 31st of December, then can you guys come tomorrow? Or will you guys come tomorrow on 31st at 7 p.m. to revise the power plant subject? Because today's response is very bad. Okay? Only question session कब शुरू होगा बेटा? होगा में, don't worry. Don't worry, it will be there. अभी बहुत समय बाकी है for only questions. Okay, it will be there. अभी it is more than one month time left for the exam. So only question session will be there very soon. So my dear, please promise me everyone that you guys will come tomorrow, that is on last day of the year of 2020, for the revision of power plant session. Okay, because tomorrow the last day of the revision. Clear everyone? That is, tomorrow we'll be revising the power plant subject at 7 p.m. Till then, take care everyone and have a good day. And if you have liked the session, then also please like it, share it, and subscribe the channel and press the bell icon. So thank you so much and have a good day. Thank you everyone.